Welcome to this problem walkthrough where we'll explore the solution to LeetCode problem number 108, Convert Sorted Array to Binary Search Tree. This is a fascinating problem that highlights the importance of binary trees and recursion in algorithm design. Let's dive in to understand the problem and solve it step by step. In this problem, we are tasked with converting a sorted integer array into a height-balanced binary search tree. A binary search tree, or BST, is a tree structure where for each node, all elements in its left subtree are smaller than the node, and all elements in its right subtree are larger. The additional requirement here is that the tree must be height-balanced. This means that for every node, the depth, or height, of its left and right subtrees cannot differ by more than 1. The input to the problem is a single integer array, nums, where the elements are already sorted in ascending order. The output is the root of the height-balanced binary search tree that you construct. Let's start by looking at an example to better understand what the output should look like for a given input. For the first example, the input array is -10, -3, 0, 5, 9. One possible height-balanced BST that can be constructed is shown here. The root node of the tree is 0, which is selected to ensure the tree remains balanced. The left subtree of the root is rooted at -3, and it contains -10 as its left child. On the right side, the subtree is rooted at 9, which has 5 as its left child. Notice how the tree satisfies the height-balanced condition because the depth difference between the left and right subtrees of every node is at most 1. The output representation of this tree as an array would be 0, -3, 9, -10, null, 5, where null indicates the absence of a child. Now, consider a simpler example with the input array 1, 3. Here, the tree has just 2 nodes. One possible height-balanced BST has 3 as the root node and 1 as its left child. The tree is still height-balanced because the difference in height between the left and right subtrees of the root is exactly 1. The array representation of this tree is 3, 1. This example highlights how smaller inputs can lead to simpler tree structures while still adhering to the rules of a binary search tree and maintaining the height-balanced property. To further clarify the requirements, let's discuss some specific constraints and edge cases that the algorithm must handle. First, if the input array contains only one element, the output must be a tree with a single node, where that element is the root. For example, given 1, the output would simply be 1. For arrays with 2 elements, the smaller element should be placed as the left child of the root. For instance, with 1, 2, the resulting tree would have 2 as the root and 1 as its left child, represented as 2, 1. The algorithm must also be efficient enough to handle large arrays with up to 10,000 elements. Finally, the solution must correctly handle negative numbers, ensuring they are placed appropriately in the BST. For example, given -3, -2, -1, the tree would place -2 as the root, with -3 and -1 as its left and right children, respectively. These edge cases ensure the algorithm works for a wide range of inputs, including small arrays, large arrays, and arrays with negative values. To solve the problem of converting a sorted array into a height-balanced binary search tree, several approaches were considered. One of the simplest is the brute force approach. Here, you iteratively construct the tree by inserting each element from the array into its correct position in the BST. While this method builds a valid binary search tree, it has significant drawbacks. First, it does not inherently ensure that the tree is height-balanced. To achieve balance, you would need to add additional rebalancing logic, which increases complexity. Second, the time complexity of this approach is not optimal. In the average case, inserting elements individually takes O and log n, but in the worst case, such as when the tree becomes skewed, the complexity can degrade to O n squared. These limitations make the brute force approach less suitable for this problem. A more efficient approach is the divide and conquer strategy. The key idea here is to leverage the sorted property of the array to build a height-balanced binary search tree recursively. By selecting the middle element of the array as the root, you naturally divide the array into 2 halves. The left half forms the left subtree, and the right half forms the right subtree. This guarantees balance at each level because the depth of the left and right subtrees will differ by at most 1. The algorithm works by first finding the middle element of the current array segment and then creating a tree node with this value as the root. Next, you recursively apply the same process to the left and right subarrays to construct the subtrees. The recursion stops when the subarray is empty, at which point you return none. This approach is highly efficient, with a time complexity of O(n), because each element is processed exactly once, and a space complexity of O(n), due to the recursive call stack. There is also a variation of this method that uses an iterative simulation of divide and conquer. Instead of recursion, it uses an explicit stack to manage subarray indices. While this avoids the space overhead of recursion, it introduces additional implementation complexity and offers no significant performance advantage in this case. Among the approaches we considered, the recursive divide and conquer strategy was chosen as the most effective solution for this problem. This strategy has several advantages. First, it is simple and intuitive, as the recursive process mirrors the natural structure of the problem. Second, it inherently guarantees that the resulting tree is height balanced by always selecting the middle element as the root. Third, it achieves optimal time and space complexity of O(n), making it highly efficient. While recursion does have limitations, such as the risk of stack overflow for very large inputs, these constraints are not a concern for typical competitive programming scenarios where the input size is limited to n less than or equal to 10,000. Other approaches, like brute force, were ruled out due to inefficiency and the lack of balance guarantees. Similarly, the iterative divide and conquer method was not selected because its added complexity in managing the stack outweighs any benefits. Overall, the recursive divide and conquer approach effectively balances simplicity, efficiency, and correctness for this problem. To solve the problem of converting a sorted array into a height-balanced binary search tree, we use a recursive divide and conquer approach. The key insight here is to ensure that the tree remains height-balanced, which means the depth of the two subtrees of every node differs by no more than 1. The intuition is straightforward. Since the array is sorted, we can make the middle element the root node. This ensures that the left and right halves of the array become the left and right subtrees, respectively, keeping the tree balanced. The algorithm begins with a base case: if the input array or subarray is empty, we return none. This stops the recursion when there's nothing left to process. For the recursive step, we calculate the middle index of the current subarray, which is determined as left plus right, //2. This middle element becomes the value of the root node for the current subtree. By constructing nodes in this manner, we guarantee the tree's balance at every level. Once we've identified the middle element and created the root node, the next step is to construct its left and right subtrees. For the left subtree, we recursively call the function for the left portion of the array, from the current left index up to mid 1. Similarly, for the right subtree, we make a recursive call for the array segment from mid plus 1 to right. These recursive calls break the problem into smaller subproblems, gradually building the tree from the bottom up. After constructing the left and right subtrees, we attach them to the root node. Finally, we return the root node of the constructed subtree. This process repeats until the entire tree is built. By always choosing the middle element as the root, we ensure that the left and right subtrees are roughly of equal size, maintaining the height-balanced property. This approach systematically guarantees that the resulting tree satisfies the problem's requirements. The divide and conquer strategy is naturally suited for this problem because the sorted structure of the array allows us to efficiently partition it into smaller segments. Each recursive call halves the size of the problem, leading to a time complexity of O(n), as each element is processed exactly once to create a tree node. Additionally, the algorithm is space efficient since it does not require the creation of new arrays. Instead, we pass the indices left and right to define subarrays during recursive calls, minimizing memory overhead. The tree nodes themselves are represented by a simple tree node data structure, which includes 3 attributes: val, the node's value; left, a pointer to its left child; and right, a pointer to its right child. By leveraging the input array and the tree node structure, the algorithm achieves both simplicity and efficiency. Now let's analyze the computational complexity. For time complexity, the algorithm processes each array element exactly once to create a corresponding tree node, resulting in O(n) time overall. For space complexity, the key factor is the recursion depth, which corresponds to the height of the tree. Since the tree is height balanced, its height is logarithmic relative to the number of nodes, leading to a space complexity of O log n. This makes the algorithm highly efficient for large input sizes. To see how this plays out concretely, we'll walk through an example using the input array nums equals -10, -3, 0, 5, 9. The goal is to construct a height-balanced binary search tree step by step. We start by identifying the middle element of the entire array, which is at index 2. This gives us the root node with a value of 0. We then recursively construct the left and right subtrees. For the left subtree, we focus on the subarray -10, -3. The middle element here is -10, which becomes the root of the left subtree. Since there are no elements left on its left, the left child is none. The right child is derived from the remaining element, -3. For the right subtree, we focus on the subarray 5, 9. The middle element, 5, becomes the root of the right subtree, with its right child being 9 and no elements on the left. Finally, we attach the constructed left and right subtrees to the root node 0. The resulting tree has 0 as the root, -10 and 5 as its left and right children, and -3 and 9 as their respective children. This height-balanced binary search tree satisfies all the problem's requirements. This solution converts a sorted array into a height-balanced binary search tree, BST. Here's how the implementation works. 1. Tree node class. A simple class is defined for tree nodes, with attributes for the value, val, left child, left, and right child, right. 2. Base case. In the sorted array to BST method, the base case checks if the input array nums is empty. If it is, the function returns none, signaling that there are no nodes to add in that part of the tree. 3. Middle element is root. The middle index of the array is calculated using len nums //2. The middle element ensures that the left and right subtrees are approximately equal in size, maintaining the height balance. 4. Create root node. A new tree node is created, initialized with the value of the middle element, nums, mid. 5. Recursive construction of subtrees. The left subtree is constructed by passing the left half of the array, nums, mid, to a recursive call. The right subtree is constructed by passing the right half of the array, nums, mid +1, to another recursive call. 6. Return the root. After constructing the left and right subtrees, the root node is returned, which now represents the root of the balanced BST. This divide and conquer approach ensures that the tree is height balanced because the array is split into two halves at each step. The time complexity of the algorithm is O(n), where n is the number of elements in the array, as each element is processed once. The space complexity is O log n, due to the recursive stack depth, which corresponds to the height of the tree. Here, we start by defining a class called solution that contains all the methods needed to solve the problem. Inside it, we define a nested static class tree node to represent the structure of a node in our binary search tree. Each node will contain an integer value, val, and two pointers, left and right, for the left and right child nodes respectively. The constructor initializes the node with a value and sets the children to null. Next, we define the main method, sortedArrayToBST, which takes a sorted array of integers as input. The first thing we do in this method is handle the base case where the input array is null or empty. If that's the case, we return null since there's no tree to build. Otherwise, we call a helper method, buildBST, which will recursively construct the binary search tree. This method is passed the array along with two indices, left and right, to indicate the current range of the array being processed. In the buildBST method, we first handle its base case. If the left pointer exceeds the right pointer, it means there are no elements left to process in the current range, so we return null. Next, we calculate the middle index of the current range using the formula left plus right left /2. This ensures that the tree remains balanced as we select the middle element to be the root of the current subtree. We then create a new tree node with the value at the middle index. After that, we recursively build the left and right subtrees. For the left subtree, we use the range from left to mid 1, and for the right subtree, we use the range from mid +1 to right. Finally, we return the constructed root node, which links the entire tree together as the recursion unwinds. To begin, we are given the input array 1, 2, 3. Since the array is not empty, we can proceed to find the middle index, which is 1, calculated as the length of the array divided by 2. The value at this index is 2, which becomes the root of our binary search tree. We create a tree node with this value. Next, we focus on building the left subtree of this root. The left subarray consists of elements before index 1, which is 1. We make a recursive call with this left subarray. Now, for the left subtree of the node with value 1, the input array is 1. The middle index is 0, and the value at this index is 1. We create a tree node with this value. Since there are no elements before or after index 0, both the left and right subtrees for this node will be none. With the left subtree complete, the node with value 1 has no children. We now turn our attention to the right subtree of the root node. The right subarray contains elements after index 1, which is 3. We make a recursive call with this subarray. For the right subtree of the node with value 3, the input array is 3. The middle index here is 0, and the value at this index is 3. We create a tree node with this value. Similar to the previous step, since there are no elements before or after index 0, both the left and right subtrees for this node will also be none. With that, the node 3 has no children. The final tree structure for this example is a balanced binary search tree with 2 as the root, 1 as the left child, and 3 as the right child. In our second example, the input array is -10, -3, 0, 5, 9. The middle index is 2, and the value at this index is 0, which becomes the root of the tree. We create a tree node with this value. Next, we focus on the left subtree of the root. The left subarray contains elements before index 2, which is -10, -3. We make a recursive call with this left subarray. For the left subtree of the node with value -3, the input array is -10, -3. The middle index here is 1, and the value at this index is -3. We create a tree node with this value. The left subarray, containing elements before index 1, is -10, so we make a recursive call with this subarray. For the left subtree of the node with value -10, the input array is -10. The middle index is 0, and the value at this index is -10. We create a tree node with this value. Since there are no elements before or after index 0, both the left and right subtrees for this node will be none. Returning to the node -3, the right subarray contains no elements, so the right subtree is none. Shifting focus to the right subtree of the root node, the right subarray contains elements after index 2, which is 5, 9. We make a recursive call with this subarray. For the right subtree of the node with value 9, the input array is 5, 9. The middle index here is 1, and the value at this index is 9. We create a tree node with value 9. The left subarray contains 5, so we make a recursive call with this subarray. For the left subtree of the node with value 5, the input array is 5. The middle index is 0, and the value at this index is 5. We create a tree node with this value. Since there are no elements before or after index 0, both the left and right subtrees for this node will be none. With that, we have completed the right subtree of the root node. The final tree structure for this example is a balanced binary search tree with 0 as the root, -3 as the left child, and 9 as the right child. The node -3 has a left child -10, and the node 9 has a left child 5. Our final example demonstrates the simplest case, where the input array is 0. The middle index is 0, and the value at this index is 0, which becomes the root of the tree. We create a tree node with this value. Since there are no elements before or after index 0, both the left and right subtrees for this node will be none. The final tree structure is just a single node with value 0. This example highlights how the algorithm handles arrays of varying sizes, from small to large, while always maintaining a balanced binary search tree structure. The time complexity for the sorted array to BST algorithm is O(n), where n is the size of the input array. To understand this, we can break it down into smaller components. First, consider the base case where the input array is empty. In this scenario, the function immediately returns none, which happens in constant time, O(1). Next, we have the recursive calls. At each step, the function identifies the middle element of the array and splits it into two halves, one for the left subtree and the other for the right subtree. Calculating the middle index and creating the root node both occur in O(1) time. However, the slicing operations, such as nums, mid, and nums, mid plus 1, take time proportional to the size of the sliced array, OK. Since the array is divided in half at each level of recursion, the total cost of slicing across all levels is proportional to the size of the input array, or O(n). The depth of the recursion tree also plays a role in the time complexity. Because the input array is halved at each recursive step, the recursion tree has a depth of log n. At every level of this recursion tree, the total cost of slicing operations across all nodes remains O(n). Combining these factors, we see that there are log n levels, and each level involves O(n) work. When summed up, this results in a total time complexity of O(n) repeated log n times, which simplifies to O(n). Moving on to space complexity, the algorithm requires O(n) space overall. This is due to two main components, the recursive call stack and the space needed for the output tree nodes. First, the recursion depth, as noted earlier, is log n, so the call stack uses O log n space. Second, the algorithm creates a tree node object for each element in the input array, resulting in O(n) space for the tree nodes. Now, let's address the space usage of the array slicing operation. When the algorithm slices the input array into smaller subarrays, those subarrays are temporary and only live for the duration of their respective recursive calls. Since they are not stored persistently, they do not contribute to the overall space complexity. Therefore, the total space complexity is dominated by the output tree nodes, which require O(n) space. Comparing this approach to a naive alternative highlights its efficiency. A naive method might involve inserting elements one by one into a binary search tree. For a sorted input array, this would have a time complexity of O(n) log n, because each insertion into a balanced tree takes O log n time, and there are n elements to insert. The current algorithm, however, avoids this repeated insertion process by using a divide and conquer strategy to directly construct the tree in O(n) time. This ensures that the tree remains balanced without additional balancing operations. To summarize, the sorted array to BST algorithm achieves a time complexity of O(n), where n is the size of the input array. The space complexity is also O(n), with O log n attributed to the recursive call stack in O(n) for the output tree nodes. This divide and conquer approach is optimal for constructing a height-balanced binary search tree from a sorted array. By leveraging the middle element of each subarray as the root, the algorithm ensures balance and eliminates the need for costly insertion-based balancing operations. This optimized approach is significantly faster than the naive alternative, making it well-suited for this problem. When working on this problem, there are some common mistakes to watch out for. First, failing to consider all subarray ranges can lead to issues. If your base case doesn't properly terminate the recursion when start-end, you might end up with runtime errors or incorrect tree construction. Next, an imbalanced tree can occur if you choose the wrong midpoint, like always picking start or end instead of calculating start plus end //2. This defeats the purpose of creating a balanced tree, as the height becomes suboptimal. Another frequent mistake is modifying the input array, such as slicing it repeatedly. This increases space complexity unnecessarily. Instead, you should use index pointers like start and end to define subarray ranges without duplicating data. Finally, overcomplicating the logic is a pitfall for beginners. Iterative solutions with explicit stack management are valid but can be error-prone. A recursive approach, in contrast, is both simpler and more intuitive for this particular problem. Ignoring edge cases is another mistake to avoid. For example, you should account for scenarios like an empty input array, a single element array, or arrays with duplicate elements. Testing these edge cases ensures your solution is robust. Now let's discuss some insights relevant to interviews. This problem is a classic test of recursion and divide and conquer principles. By consistently selecting the middle element as the root, you ensure the tree remains balanced. The optimal solution here runs in O(n) time, as each element is processed exactly once during the recursive tree construction. Space complexity, however, is O log n due to the recursion stack depth. Additionally, this problem connects to other divide and conquer challenges, such as finding medians or constructing trees from sorted data. If you're solving this in an interview, focus on clearly explaining your thought process. Emphasize how choosing the middle element guarantees balance, and discuss the pros and cons of recursive versus iterative approaches. This problem also shares similarities with a number of related questions. For instance, LeetCode 109 deals with converting a sorted linked list into a binary search tree, which is a variation that introduces additional complexity. LeetCode 1382 focuses on balancing an already constructed binary search tree, while LeetCode 95 explores generating all unique binary search trees for n values. These problems build on similar concepts, so practicing them can strengthen your understanding. In terms of alternative approaches, you could consider using an iterative method. Here, a stack is used to simulate recursion, dividing the array iteratively while constructing the tree. While this avoids hitting recursion stack limits, it tends to make the code more complex. Another alternative is in-place construction, where you define subarray ranges using index pointers like start and end rather than creating new subarrays. This approach is more space efficient but might be less intuitive for those new to the problem. Finally, you might explore using balanced tree libraries, such as Python's sorted dict, to automatically create balanced binary search trees. This is the easiest solution to implement, as the library handles the balancing logic for you. However, relying on such libraries may not demonstrate your algorithmic thinking, which is often the focus of coding interviews. While libraries can be useful in real-world applications, make sure you understand the underlying principles of tree construction, as interviewers are likely to assess your ability to implement these concepts manually. Balancing ease of implementation with demonstrating your understanding is key when deciding how to approach the problem. Great job! To wrap up, we learned how to convert a sorted array into a height-balanced BST using recursion. Remember, mastering recursion and divide and conquer techniques is key for tree-based problems. Thanks for watching, and see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!